All right, so we're going to be going through 5.7 Pythagorean Theorem in this video. So hopefully remember that the Pythagorean Theorem is a relationship that is for right triangles. So if we have a right triangle, then a squared plus b squared will always equal c squared, where c is our hypotenuse, a and b are the legs of the right triangle. Pretty simple relationship, something that you've used before, I'm sure, and we've used in this class even. So hopefully you're familiar with that. A and B, the legs are interchangeable in our formula. It doesn't really matter which leg we make A and which leg we make B, but it does matter that the hypotenuse is C. Pythagorean triples, this is something that's a little bit extra, but worthwhile to know. There are a lot of these Pythagorean triples, and so a Pythagorean triple is a set of three whole numbers that satisfy the Pythagorean theorem, meaning that they actually make a right triangle. So the smallest of the Pythagorean triples here is 3, 4, 5. So you can kind of check it out here. 3 squared is 9, plus 4 squared is 16, and 5 squared is 25. So in this case, right, adding those together, we do actually get 25. So 3, 4, 5 will always make a right triangle if we use those. Also, any multiple of 3, 4, 5 will also make a right triangle. So if I multiply these all by 2, 6, 8, 10 is another Pythagorean triple. Or if I multiply these all by 3, that would be 9, 12, 15 is a Pythagorean triple. If I multiply them by 4 or by 5 or 6 or 7 or 8 or 9 or 10, any multiple of 3, 4, 5 is also a Pythagorean triple. And then we have these other ones. These are all what are called relatively prime Pythagorean triples, meaning none of these later ones are just a multiple of 3, 4, 5, and none of these are later ones are a multiple of 5, 12, 13, and so on, right? They're their own sort of unique Pythagorean triple. So 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25, 9, 40, 41. After that, they start to get pretty big, but obviously any multiple of any of these would also work. So a multiple of 5, 12, 13 would also be a Pythagorean triple. So if you multiply these all by 2, you could get a 10, 24, 26. That would also be a Pythagorean triple. What's the point? It just sort of saves you some work, right? If you notice your problem is a Pythagorean triple, you don't even have to use the Pythagorean theorem, right? Something to be a little careful of, right? If you look at the problem and you have two of the sides and you say, okay, I notice that this is a 5 and a 3. So I know that this is going to be a 4 because this is a Pythagorean triple. But if it's a little different, there's this temptation to over-apply Pythagorean triples. So like if this one is 4 and this one is 3, a lot of people are going to be tempted to say that this side is 5 because it's a 3, 4, 5. This can't be 5 because the hypotenuse is the longest side. This can't be 5 because 5 is bigger than that, right? That biggest side in our triple has to be the hypotenuse. So since 4 was the hypotenuse, this is not going to be a 3, 4, 5 triangle. It's some other triangle. So be careful when you're applying Pythagorean triples, but they can save you some work. Well, when we don't have a Pythagorean triple, we're going to have to be simplifying radicals. So simplified radicals are something that we do to get our answer in sort of a consistent form. And so what we mean by a simplified radical form is that there are no more perfect squares that are a factor of the radicand. The radicand is the number that's inside the radical. So here's an example of this process. So we have simplified the square root of 32 into this. 32 has 16, which is a factor. 16 is a perfect square number. So this is not in simplified radical form. This is in simplified radical form because the radicand has no perfect square factors other than 1. Every number has a factor of 1. So it would be impossible to simplify if we included 1 in that list. What I mean by perfect square numbers, right, are like 2 squared is 4. So 4 is a perfect square number. Or 3 squared is 9. That's a perfect square number. Or 4 squared is 16, and so on, right? These are the perfect square numbers. And obviously, they keep going beyond that. So here's the process of simplifying the square root of 32. This is just one way to do it. This is the way that I'm going to teach it, but if you have a different method, feel free to continue using that. So I like to look at my number, find the largest perfect square factor that's a factor of that number, factor it. So 32 is equal to 16 times 2. That's the biggest perfect square number that is a factor of 32. Square roots allow us to split anything up that is multiplied together into two separate square roots. And then the square root of 16 becomes 4. And the square root of 2 is irreducible from there, so we have to just leave it. So the square root of 32 is actually equal to 4 square root 2. We're going to go through this process in several examples on the next slide. So if you're not getting it yet, that's fine. Just hold on, see if it makes more sense later. All right, so let's go ahead and take a look at these. If you want to pause it right now and kind of try these on your own and then look back at what I'm doing, feel free to do so. I'm just going to go ahead and go through them. So we're looking at the square root of 28. So for this, I like to list out my factors for 28. How can I multiply and get 28? 1 times 28. This first factor that you can always write for every number is not going to be useful. We are going to ignore 1 as a perfect square in our factoring, because if we split this up as the square root of 1 times the square root of 28, and then turn that into a 1, well, that doesn't really get us anywhere, does it? We still have the number 28 and just we haven't made any progress on this. So we're not going to include 1 as a perfect square factor. So we can kind of ignore that factoring right off. But then we have 2 times 14. Neither of these are perfect squares. And then 4 times 7. 4 times 7 is golden. That's great, because 4 is a perfect square number. So 4 is a nice one. And then there's no other factoring. So 4 is the biggest. So square root of 28 is equal to square root of 4 times 7. Again, we can split that up. Square root of 4 times the square root of 7, which becomes 2 times the square root of 7. And that is our final answer. This is in reduced radical form or simplified radical form. 7, the number inside here, has no perfect square factors other than 1, so it's reduced. All right, let's go ahead and look at the next one. The next one has a pretty big number in there, but it's a nice number, 200. We could go through and list all the perfect square factors. We know that 4 will work, 4 times 50. So 4 is an option, but we want the biggest. Maybe there's a bigger one. Also 25. 25 works, right? 25 times 8. Yeah, times 8. So that's a pretty big one. Can we go any bigger than that? 36, no. 49, no. 64, no. 81, no. 100. 100 works, right? 100 is very big. That's actually going to be the one we want. 100 times 2. That's the biggest perfect square factor, so that's the one I want to choose. 100 times 2. Split that up. Square root of 100 times the square root of 2. Square root of 100 is 10. 10 times the square root of 2 is our answer. Again, we can simplify this a little bit. We may not need to do both of these steps. We could probably write this one out here and kind of skip over this step. But I'm kind of showing the whole process. All right, last one, square root of 75. So the square root of 75, so again, we're going to look at all the numbers that are factors of 75 that happen to be perfect squares. So we could kind of go through them and look at all of our options. So 4 is not a factor, 9 is not a factor, 16, okay, 25 is a factor, right? 25 times 3. So that's an option. And actually, we already know this one, this is going to be the best. So if you look at the other number and there's no perfect square number that's a factor of this, then that's going to tell me this is the biggest one. So right here, if I look back here, I know that 25 is not going to be the biggest one because 4 is a factor of 8. I have a perfect square factor left in here. So I know that's not going to be the biggest one, just as an example. But there's no perfect square factor for 3, so I know this is the best we can do. So square root of 25 times the square root of 3. Square root of 25 is 5, so it's 5 square root of 3. That is our final answer. The more you do these, sort of the faster you get. Obviously, these numbers are not too big, and they can actually get fairly large when we're doing Pythagorean theorem. We could end up with large numbers, so we may need to end up relying on a calculator to do some of these for us. All right, let's move forward. All right, I love this visual for remembering about the hypotenuse. Oops. So the hypotenuse. Remember, when you're setting up Pythagorean theorem, the C always has to be the biggest side, always has to be the hypotenuse. Okay, if you forget that, if you mess that up, it's totally going to give you the wrong answer. So be careful with that. Sorry, a little hot in here. Okay, next, let's go ahead and do some examples here using our Pythagorean theorem. So we're going to solve for the missing side. I'm going to talk through it. First off, the way I want to do this right away is just make sure I know where the hypotenuse is. Hypotenuse is always across from the right angle. It's the longest side. So this one is our hypotenuse. A and B are interchangeable. It doesn't matter which of these I call A and which one I call B. I'm just going to set it up like that. Okay, so it's A squared plus B squared equals C squared. 10 squared plus 24 squared equals C squared. That's 100 plus 576 equals C squared. So that's 676 equals C squared. And then we have to take the square root to get our final answer. Now, hopefully this is a nice perfect square. I don't have to memorize this high. I'm using my calculator, square root of 676. It is. It's a nice one. We got 26. Okay, so 26 is equal to C. If this was not a perfect square and we had to actually reduce it, which we will in the next one here, I believe, we'll have to talk about what to do, especially for really big numbers like this. So. Okay. All right, problem number 2. Let's go ahead and look at this one. Again, the way I want to start is identifying my hypotenuse. So the hypotenuse is across from the right angle. Right here, it's the 24. A and B are interchangeable, doesn't matter. We'll call this one A and this one B. So in this case, it's a little different. We're not solving for C, we're actually going to be solving for A. So we have A squared plus 6 squared equals 24 squared. Okay, A squared plus 36 squared. Nope, why did I write squared? Plus 36 equals 576. Now to solve for A here, we need to get rid of that 36. So subtract 36 on both sides. That's going to give us that A squared equals 540. All right, 540. I don't believe that's a perfect square number, so 540. Yeah, that's not a perfect square. I get this decimal right here. So I'm going to have to simplify this when I take the square root. So let's look at 540. So perfect square numbers I want to be trying, right? 16, 25, 36, 49, 64, etc. Let's go ahead and divide this. Let's see, 540 divided by 4. Okay, so 4 works. 4 times 135. Okay. 540 divided by 9. Okay, 9 works. So both of those work. Interesting. I know this is not going to be the biggest, though. I'm already on to it. 9 is not going to be the biggest because 4 is a perfect square number, and that's a factor of 60. So there's something bigger than 9. So we got to keep going. 540 divided by, okay, 16 is not divisible, so 25 is not going to work. Okay, 36 worked. 36 times 15. I know this is the biggest. 36 is the biggest because 15 has no perfect square factors. None of the numbers here, 4 or 9, work. So this can be done as the square root of 36 times 15, which simplifies to 6 root 15. So that is our missing side there, 6 root 15. nice. It can be pretty difficult, these problems, but you know, all I did was sit here and try to divide 540 by all of these perfect squares until I found a big one that worked nicely, right? So not too bad. And yeah, and also a lot of calculators can actually do this for you. So this calculator I was holding back can actually reduce it. Hopefully you can see that, but 6 root 15. A lot of scientific calculators can simplify radicals for you. And there are some good ones online. If you look for simplifying square root calculator, you can probably find a good one online as well. All right, so another way that we can use the Pythagorean theorem is you can determine if 3 sides will actually make a right triangle or not. You just see if they satisfy the Pythagorean theorem. See if when you do a squared plus b squared, it does in fact equal c squared. If it does, then it's a right triangle. If it doesn't, it's not. So let's go ahead and try that. So if we do this, 4 squared plus 12 squared, let's see if that equals 16 squared. 4 squared is 16, plus 12 squared is 144, and 16 squared is 256. That's not going to work because this is only 160. So these are not equal. So this is not a right triangle. Simple as that. Wasn't equal, it's not a right triangle. Let's try the next one. 7 squared plus 24 squared equals 25 squared. Remember, the biggest side has to be C. Has to be the hypotenuse. All right, so this is 49 plus 576 equals 625. Adding those together, I'm going to use my calculator. 49 plus 576. Yep, 625. Check, works out. So this is a right triangle. These sides would actually make a right triangle. It's that easy. If they satisfy it, if they are actually equal according to the Pythagorean theorem, sorry, if they're not equal according to the Pythagorean theorem, then it's not a right triangle. If they are equal according to the Pythagorean theorem, then it is a right triangle. Not too hard, it's just another way that we can use it. And then the last way to use it is, what about those non-equal ones? Can we tell any more information about it? Can we decide if they're acute or obtuse? Yeah, we can. Turns out, if c squared is greater than a squared plus b squared, it's obtuse. So if it's greater, if the hypotenuse is greater, then it's obtuse. I like to think about this similar to sort of our hinge theorem, right? If we have a right triangle, right triangle here, if that hypotenuse is too big, it has to open that hinge more than a right angle, making it obtuse. If that hinge is too small, meaning the hypotenuse is too small, it makes an acute angle. So there we go. If it's too small, it makes an acute triangle. If it's too big, it makes an obtuse triangle. So let's examine these 3 lengths, see what type of triangle they make. 8 squared plus 10 squared. We don't know if it's bigger or less than, but we're going to compare it to 16 squared. See, that's 64 and 100. So that's 164, and this is 256. So the hypotenuse is too big. It's bigger than the leg squared. So this is going to be an obtuse triangle. Kind of a simple application. Remember, if it's just right, it makes a right angle. If it's too big, it opens up that hinge, makes an obtuse angle. And if it's too small, closes that right angle down, makes it an acute triangle. That's one way to think about it, one way to remember it. All right, good luck with the homework, guys. I'll see you guys in the next one.